Okay, I think we can already start. So welcome everybody. It's a pleasure to celebrate. I think it's our last webinar since the project is coming to an end. We will also have our final event in the upcoming months, but this is like one of the last webinars that we are celebrating. So I hope you enjoy. And let me briefly explain the agenda that we will conduct. Well, my name is Pablo Morales from Sustainable Innovations, and I will be moderating the session during the webinar. As I said, the webinar started now at 10, and during 5-10 minutes, I will explain the structure of the webinar. In the first place, Elizabeth Ayerbe from our coordinator entity, CIDETEC, she will be giving a full overview of the Defacto workflow, not only the software developed, that it will be explained by Ruth Medeiros. She will explain the overview of the developed software specifically. And then we will have the opportunity to explain a tutorial or some guidelines about how to use this software, and it will also explain it by Eduardo Jané. Both are from Polytechnic University of Madrid. And then I will proceed with a Q&A in order to know a little bit more about our audience, and also to give you the possibility to interact with us in case that you want to ask something or comment something regarding the webinar. So some notices before we start. The session is being recorded, so in case that you want to double see the session, it will be uploaded in the Defacto website in the upcoming days, probably during this week. So for that reason, the session is being recorded. Make sure that your microphone is muted. I think by default you cannot activate it, but if you want to use any, if you want to ask specifically something, I will be taking care of the chat. So feel free to use the chat to enter your questions or comments, since I will be reading and I will be addressing your comments or questions to the corresponding speaker. And last but not least, since we don't want to have like a boring meeting, so we want to make it interactive, we will be conducting an interactive session through Mentimeter. So make sure you have your phone with you, since I will be sharing a link where you can participate in the upcoming question that I will be asking. So I think now I already introduced myself. I'm communications manager here at Sustainable Innovation, and in particular in Defacto, I'm dealing with the communication and dissemination, which includes this kind of activities such as the events, but we are also taking care of the website, social media, basically spreading out all the results that all the technical partners are carrying out during the project. Now I would like to give the floor to Elizabeth. Maybe you, Elizabeth, want to introduce yourself a little bit?
Okay, yes, thank you, Paulo. So I'm Elizabeth Ayerbe. I'm team leader in modeling and postmortem at CIDETEC Energy Storage, and I'm coordinator of the Defacto project together with my colleague Maria Icane.
Should I introduce myself as well? Okay, yeah, so I'm Eduardo Jané. I'm a researcher at Polytechnic University of Madrid, and I've been working in the Defacto project full-time on the development of time-adaptive reduced order models.
Thank you, Eduardo. And Ruth, if you want to say a few words.
Yeah, good morning to everyone. My name is Ruth Medeiros, and I am a researcher too at the Universidad Politécnica de Madrid. And I'm currently working the application of reduced order model to accelerate the optimization applications.
Thank you, Ruth. So following the agenda, I think now I will give the floor to Elizabeth to explain the overview of the Defacto workflow. So Ellie, let me stop sharing.
Okay.
Now the floor is yours.
So I guess you can see my slides.
Yes.
Yes.
Okay, and I will also include the laser just in case. Okay, so as I was saying, I'm the coordinator of the Defacto project that it's currently on the month, approaching to the month 42, so coming to the end, in the end of this year. So the main purpose of today's webinar is to introduce you our work on the Defacto workflow, give us a general overview of what we've been working on. So let me start saying the main aspects that we will be introduced today. So first, a general overview on the motivation of the study. Then Defacto is dealing mainly on the models and developing tools for manufacturing and also cell design. So I'll give information on the multiphysics models that have been already developed within the project. Then the work that is being carried out currently on the workflow for this specific target on the cell design and manufacturing, and then some keywords on the conclusion side. So let me start saying that the main motivation and aspects that we came when we were writing the proposal is to somehow to develop tools to enhance and accelerate the manufacturing process. So this was the main target of the topic itself, that it was written previously, and the project was started in 2020, beginning of 2020, before the pandemic. So basically what we aim is to reduce the time to develop cells and even the cost, very much focusing on the manufacturing, not only on cell design, and even coupling cell design together with the manufacturing, so that we can know in advance each of the manufacturing process, how can impact the cell performance and cell aging. Obviously, this implies to somehow reduce the battery R&I cost to a certain amount, and obviously to try to extend the durability and lifetime of these cells by correlating to the manufacturing. So all in all, the main target of having these tools is to speed up the manufacturing process, which indeed it's a really complex process. So yeah, this is the main scheme of the Defacto project, that if you have already involved in any other webinars we might been doing, you might be aware, but it's very much focusing on the modeling side. We have a different work package in which we are developing different tools for capturing electrode processing, electrode filling, and also electrode cell performance and cell aging models. So this is very much the main, the core activities within the project, but we cannot forget about all the characterization and prototyping work, because without the real cell, we wouldn't be able to calibrate and validate the tools. So yeah, even though the main aspects and the main contribution is on the modeling, we cannot forget all these activities on the characterization and prototype, as I was saying. And there are different chemistries that are already been in place in the Defacto. So we are jumping from the NMC 622 graphite technology to nickel-rich or higher nickel content cathode material and graphite with or composite graphite silicon anode. And then something in which we might be also working is to provide certain guidelines, or even to see how we can transfer the knowledge we have gained and then tools we have gained within the project to different technologies, like or different chemistries like the LMNO and graphite silicon, as pointed out here. So yeah, regarding the physics-based tools that are already developed within the project, we are very much focused. I mean, cell manufacturing is really complex, but when it comes to the electrode in particular, there are different steps in which are very much interconnected somehow, and each of the individual steps might be impacting on the final result. So at the electrode, we will be focusing very much on the electrode production, and then also on the filling aspects while we are talking on the manufacturing. So coming to the electrode productions, we will be dealing with we are already, it's on the mixing or dispersing step, and then there's very much focused on the drying step, and the final step in the electrofabrication is in the calendering. And while we are talking about this cell assembly or cell finishing steps, we will be working on the models capable to reproduce the filling step and somehow optimize this procedure, and then very much on performance and including aging. And then the idea behind this, it was to also to work on the optimizations, because somehow this give you on the best cell properties or electrode configuration or electrode properties that might need this cell in order to enhance the durability. But it's not only about that. It's not only about optimizing or identifying this best cell electrode parameters. It's also connecting these parameters to the manufacturing steps. So this is the main target, and this is a very complex procedure, but we are on a good shape, and I would say on good track and reaching the target. So yeah, coming to the physics-based tools, as I was saying, that we are very much focused on electrode processing, but also in the filling step. So our partners like TU Braunschweig has been leading these 3 steps models in which they are working. They have already developed a tool so that they can mimic, or they can identify the best agglomerate size depending on the shear stress in this dispersing or mixing step, wet mixing procedure. Then jumping to the drying step, they have developed a CFD-DM simulation, and then they can predict the certain properties of the electrode, like the thickness and porosity, depending on the drying parameters, which is a very complex step, so might be impacting very much not only on the performance but also on the aging, depending on these specific parameters, as well as the active material distribution. And then finally, they've been working on the calendering, developing DEM simulation tools in order to replicate the impact of the certain calendering parameters like the compaction or pressure parameter onto the final density or mass loading of the electrode together with the final porosity. So this is very much important, but not only this, because what we are doing currently is to connect this final electrode configuration to the filling procedure step in a way that they have already developed tools. They are like different high fidelity tools so that they can predict certain or identify the best filling process parameters to predict final performance, like pressure saturation, or how gas entrapment might impact and so on. So they have already DLR, it's in charge of the filling procedure, and then they have developed different fidelity models in order to replicate these steps. And what we are now currently working on is linking these two let's say, approaches, the final electrode configurations together with the specific identifying best filling procedure. Not only about models, and what we are doing is to somehow connect the models to the reality, and also what we are working on, in particular, what Earth is doing is that they are validating the digital electrodes together with experimental by different techniques, and they have reconstruct and they have developed tools in order to replicate in the 3D domain the experimental data. So and also here, it is related to the fidelity of the tools that now currently they have developed, as I was saying, different fidelity tools in order to replicate this specific step in the filling, and by means of these tools, they are able to identify best filling procedure steps. So this is related to the manufacturing, while then we are somehow connected to cell performance, and within the Defacto, we are also covering multi-scale approach in the cell performance and aging, and we are very much emphasizing on the mechanics because one of the chemistry is being analyzed it includes silicon. So what at the atomistic scale, it's somehow what we are able to do right now is to predict mechanical electrochemical parameters in this scale at the OCPs, and then this comes into the next steps in which they have this macro scale simulation on the mechanical response, and they are able to track also and to link to the mechanical aging at these scales. And then on the continuum scale mechanics, they are including these mechanics together with the electrochemistry, and then they can, now if I maybe this way, you can see the swelling of the electron depending on the parameters of the silicon that might come from the previous scale. So this is on the continuum scale in which these are the 3D domains, while then coming to the continuum but simplified or P4D approach, we have already developed as well on the tools that are capable or efficient tools in which we are able to perform simulation of the aging of the cells. So partners involved, because I didn't say, is that Fraunhofer, CEA, UPM, AB, and CIDETEC. So the last but not least, and this is the tool that will be also presented later on, and it will be also introduced by my colleague Ruth Medeiros and Eduardo Jané from UPM later on. So basically with this multi-scale approach, we are able to capture better the mechanisms into the upper scale and to predict performance and aging. But it's not only about this performance, but also linking to the optimization. And the idea behind is we want to identify the best electrode and cell design configurations and later link to the manufacturing. So obviously before the optimizations, we have already found certain sensitivity analysis to identify if certain parameters is sensible or not, and how it's impacting on the cell performance, and then we are carrying on all the optimization. And by doing so, later, again, my colleagues from UPM will be describing the tools that has been already released as open source. So coming one of the examples of we are already working on is to track and to identify this best configuration of the cell. So in this case, we are including this specific case of the graphite NMC811 cell, and what we want to identify is the best electrode properties such as the porosity and thickness, and what and to obtain this, we have released one of these tools that will be described by UPN. So this is one of the samples, and the idea behind, as I was saying, is to link these properties to the manufacturing tools. So this is the complete workflow, and the idea is to somehow link each of the individual tools which are developed within the project together with the specific chemistry cell and specific parameters. So our main target, as I was saying at the beginning, is to provide guidance to cell design and cell manufacturing in order to accelerate the development phase. So we will start running with one sample of the cell, but once we develop everything and once we are focusing very much on the specific chemistry, the idea is to provide a new configuration of the cells by means of the modeling tools. So what we see is that there are like two directional work. We can see that there's one for one side, it's that we can predict the impact of the manufacturing process onto the cell performance, and this is the straightforward output of the Defacto. But then also what we are very much interested in is on providing guidance, how we can enhance or maximize energy density or maximize durability, and to identify which are the best parameters to manufacture it. So to obtain this, first of all, is we need to calibrate the codes and we need to validate the codes. And for that, we need to have a huge amount of information on the experimental side. So and within the project, we are working on characterization at different length scales, like the materials, electrons, and cells. And this is an ongoing task, and it's, I mean, obviously it's quite tedious because we are not only considering electrochemistry, but also mechanics. So there are a huge number of parameters to obtain within the different chemistry cells. And then obviously we need cells, and we have on board our partner Leclancher, that they have already provided industrial commercial cell, but also they are providing information on our prototype graphite silicon nickel rich cells, in which we will do cycling, and we are running tests on cycling, and then we will be doing the postmortem of the anodes to identify degradation mechanisms, and also to extract the parameters to fit the specific models capturing these specific degradation mechanisms. Also, not only about the commercial cells or industrial cells, but we have more prototype cells coming from Tubras, right, and CIDETEC. And we have already manufactured prototype graphite NMC622 cells. We are running again cycling tests. We will be doing postmortem, and then obviously extract all the parameters, which are a huge number of them, in order to calibrate the code and validate it. Then, finally, we will be also working on the prototype graphite silicon NMC811, and this is currently being assembled at CIDETEC. So coming to the workflow, we will be focusing on this specific chemistry, and mainly is because we want to make a proof of concept of this workflow, and somehow we need the data, and everything is prepared for this. I mean, the cells are assembled, we are running tests, we will be soon do the postmortem, so we expect to have everything in place in order to start running the simulation with the weak coupling of the workflow. So the workflow will be based on this technology, but nevertheless can be transferable to other chemistries, obviously. So as I was saying, there is a huge number of parameters that we need to obtain in order to have each of the models calibrated and validated. But although it's a tough and tedious work, it's been already in place, and each of the partners has a huge contribution in here. So and then one of the aspects, and once we have this information, because at this stage we have already all the models developed and implemented, and then they have already validated the code by even the own cells or cells that have been already developed in the Defacto. And now the main target is to transfer this validation to a specific chemistry cell that will be this graphite NMC622. So basically, we are very much interested not only on the first point that I was saying, that the first target of the workflow is this straightforward configuration, predicting performance depending on the process parameters, but we are very much interested in optimizing and providing guidance through an optimized electrode configuration to them, and translate this information to the manufacturing in order to identify best process parameters. So by here, we need to run this optimization simulation, and it's very much, it's really important to conduct properly with efficient codes, and this will be explained by my colleagues from UPN later on. And the main objectives with this optimization will be to try to give an answer to these three aspects, which are basically energy density, durability, and fast charging protocols. So what we want to solve is a multi-objective function in order to enhance cell performance and then try to correlate with each of the individual model parameters. So yeah, this is the current state of the workflow. Yeah, just as a conclusion is that each of the simulation tools is already in place. It has been implemented and validated, and they are ready for working or to start building this weak coupling of the workflow. And then also for the optimization tool is that the optimization, as you will be seeing later on, is that it has been already implemented and it's been again validated, in this case against literature data, but it's almost ready for being used in this workflow application. So main caveat we might have now is to validate these each individual tools for specific cell chemistry in order to build this proof of concept of accelerating the cell design and manufacturing process. So with that, I came to my end of the presentation, and then if you have any doubt, maybe you can, we can try to answer you in the end of the webinar. Thank you.
Thank you so much, Ellie. I think there was some issues with the chat, but you should be able now to enter your questions, so feel free to use it. So perfect timing, Ellie. Thank you so much. It's almost 10:30. I think it's now time to give the floor to Ruth, correct?
Yes,
She will be explaining the overview of the developed software. So the floor is yours, Ruth.
Okay, can you see my screen?
Not yet, but it says that it's sharing. Yes, let's wait a few seconds.
You cannot see it
Yeah,
yet.
yeah.
Oh, okay, sorry.
Yes, sir.
Okay, so again, good morning to everyone. My name is Ruth Medeiros, and as previously introduced, I'm a researcher at Universidad Polytechnic de Madrid. I'm going to talk about two open source software developed in the framework of the Defacto project. These two tools use physics-based modeling and model order reduction techniques following two main objectives: to predict the performance of a specific battery cell and perform the optimization of a battery cell design. To meet this objective, two software tools have been developed: the time-adaptive Defacto reduces P4D tool and the Defacto time and parameter adaptive reduce of the model optimization tool. The time-adaptive reduce P4D tool solves continuum P4D models using time-adaptive model order reduction techniques. This tool is internally organized in two independent components. The first component is called CIDEMOD and has been developed by CIDETEC. This is a simulation software able to solve a pseudo 2, 3, and 4-dimensional continuous model. And the second element is ECPROM and has been developed by UPM. This is an acceleration tool based on the use of time-adaptive reduce of the models. The distribution of the time-adaptive reduce P4D tool has been done using a free and open source software license, in particular the AGPL license. And in order to make as easy as possible the distribution of the tool, the developed package and the requirements has been released in a Docker image, which can be downloaded on the Defacto project website, together with some instructions to install Docker and with the code documentation and a code tutorial. This code tutorial is also available at the code documentation in different formats. In the figure here, you can see an example of two snapshots of this tutorial. In the upper side of the figure, you can see the description of the needed input files to use the tool, and in the lower side you can see the beginning of the description of some of these files. The code documentation has been generated using Sphinx. As you can see in this figure, the documentation is created in the function header. In the first part of the header, we add a description of the capabilities of the function, following by a list of the input required by the function with their description and types. And lastly, we add the output that the function returns. Thus, using Sphinx, the documentation of this function could look like you can see in this figure. Well, as I previously said, the first component of the tool is CIDEMod, which is a package to extend the Doyle-Fuller-Neumann model to 3D battery cell geometries. It can simulate P2D, P3D, and P4D models with the same code. In this figure, you can see a schematic of the CIDEMod package structure. As you can see, the user must provide the battery geometry, some discretization options, the material properties of the cell, and the solver configuration settings. With this, CIDEMod is able to solve thermal electrochemical models, considering also the main degradation mechanisms such as the solid electrolyte interface growth and the loss of active material. Thus, CIDEMod used the finite element method and FinFenix and Multifenix Python package to solve the simulation. The second element is ECRON, which is an acceleration tool based on the use of time-adaptive model order reduction technique to solve the P4D continuum models. The solution in this case is carried out combining the use of CIDEMod for some short periods of time and the integration of the P4D model by a reduce order model built on the fly using ECRON. In the schematic at the right of the slide, you can see how the simulation starts by solving a few time steps using the full order model. Then we switch to the reduce order model and integrate in time until the reduce order model solution loses its accuracy. We come back to the full order model to update the information needed to update again the reduce order model, and we continue integrating again and repeating the processes until the final time or the cutoff voltage is reached. The first application example consists in the simulation of the electrochemical behavior at a 0.50 rate discharge of a graphite MNC cell. In the slide, you can see the computational mesh considered to solve this problem, which has almost 200,000 finite elements. In this case, the percentage of time steps solved using the full order model is around 10%. So the reduced order model gets a speed up factor of almost 9 in simulation time when comparing to the CIDEMod simulation. But in this case, we expect a bigger acceleration speed up factor when we consider easier scenarios. The second application consists in the simulation of a 0.50 rate discharge for a different graphite MNC cell, in this case considering the electrochemical, thermal, and degradation models. In the figures at the left, you can see the computational method considered. In the middle, we show the initial electrolyte concentration at a slide of the cell defined by the plane shown in the left figure. And in the right figure, you can see the electrolyte concentration profile at a time equal to 200 seconds for the profile defined by the white line marked in the slide of the domain. We also show the same profile at the same time step for the solid phase lithium ion surface concentration in the middle and for the intercalation current density at the right. Finally, here you can see the temperature and the solid electrolyte interface thickness over the time for a particular node in the anode domain. Well, the second tool developed in Defacto is the optimization tool called Time and Parameter Adaptive Reducer Model, and it is internally organized in 3 different components: CIDEMOD, ECROM, and OptiBat. OptiBat is a Python package developed by UPM and CIDETEC to efficiently perform a cell optimization using time and parameter adaptive reducer models. The optimization tool has also been distributed using the same license as the reducer model, which was the AGPL license. And again, you can download at the Defacto project site a Docker image containing the optimization tool and all the documentation and tutorials. As before, the documentation of the optimization tool was generated using strings, as you can see in the figure. Again, first we give a describe of the capabilities of the function, following by a list of the inputs required by the function, and last we add or indicate the outputs of the function. Well, OptiBat is a Python package developed to efficiently perform the cell optimization, and it combines the use of the time adaptive before the reducer model together with a parameter adaptive strategy to accelerate the computation using information of previous reducer model. OptiBat contains the implementation of an interface to the SciPy optimization algorithms. So as effective optimization algorithms use the gradient or the derivatives of the optimization functional, OptiBat provide the possibility to compute these sensitivities of derivatives to use these gradient-based optimizations SciPy algorithms. Well, in the left part of the slide, you can see a schematic of the structure or organization of the OptiBat package. It contains 4 different modules, but the most important of them is the opt module. It has some modules as the derivatives one, which contains function to use that we use to compute the problem sensitivities. In the figure at the right part of the slide, you can see 4 different sensitivities of the problem variables corresponding to the 1C rate discharge for a graphite MNC cell. And as you can see, there is a good agreement between the reducer of the model sensitivities and the reference sensitivities, which was computed using the full of the model and finite differences method. The second submodule of this package is the param strategy, whose implement the reducer of the model parameter adaptive strategy, which aims to reduce the number of time steps solved by the full of the model to accelerate the optimization process. And this strategy use the information of previous reducer of the model to enrich the current reducer of the model and reduce the number of necessary adaptations. So in the figure at the right, a comparison between 2 optimization strategies using different reducer of the model are shown. In the left column, you can see the voltage over time at the optimization iteration for a time adaptive reducer of the model, corresponding to the maximization of the delivered energy of a graphite MNC cell during a 1C rate discharge. And in the right column, you can see the same result corresponding to the use of a time and parameter adaptive reducer of the model. Here in each figure, the shaded areas correspond to the time steps solved using the full of the model. So as can be seen, the second strategy, the one to use a parameter adaptive technique can significantly reduce the number of time steps solved by the full of the model and reduce the number of required adaptation for the reduce of the model. Lastly, the Up-Fun module includes a template for an objective function implementation. In this case, correspond to the maximization of the delivered energy for a given cell at a constant theory discharge. In the figure at the right, you can see the source code corresponding to this evaluation. The first part of the code correspond to the calling to the time adaptive reduce of the model to solve the simulation and compute the derivatives. And the last 4 lines correspond to the proper function evaluation. So as you can see, if we need to implement a new objective function, we only need to change these 4 last lines. The same happens to the derivatives computation. Here in this code, to evaluate the objective function derivatives, we only need to change the last 2 lines of this code. So implement a new objective function is that simple as change a few lines in this template. Well, to analyze the performance of the parameter adaptive strategy within the optimization, we will see the result corresponding to the maximization of the delivered energy at a 1C rate discharge for a graphite NC cell, considering in this case 4 optimization parameters: the anode and cathode porosity and thicknesses. In addition, in this case, we also consider 4 optimization constraints. We give a cell valence value, we fix the cell capacity, and we set upper and lower bounds for the porosity and thicknesses. In this figure, you can see the evolution of the objective function over the optimization iterations for the set of parameters that are indicated in the table. In this case, there is a big difference in the objective function value between the initial guess and the first optimization iteration, corresponding with different set of parameters, as you can see in the table. But in the iteration 2 and 3 of the optimization process, the parameters only made a small correction of their values, resulting in a small variations in the objective function value. In this table, you can see a comparison in computational cost of 3 different optimization strategies. The first strategy use the full of the model to evaluate objective function and use finite differences method to compute the objective function derivatives, which takes almost 400 minutes to perform the optimization. The second strategy is the pure reduce of the model, able to reduce the computational cost by a factor of 20. This factor can be increased to 30 when we add the combination of the time and parameter adaptive reduce of the model. So as you can see in the table, the full optimization cost using both reduce of the models take lower time than the evaluation of the first iteration with the full of the model strategy. To conclude, within the framework of the Defacto project, 2 efficient tools has been developed. The first one is the time adaptive reduce P4D, which achieves a speed up factor of 10 when compared to the simulation using the full of the model. In addition, this factor can be increased to 100 when we combine this reduce of the model with parameter adaptive strategies. and the time and parameter adaptive reduce of the model, as just can say, can achieve a large acceleration of the optimization process, resulting that the full optimization with the reduce of the model has a lower computational cost than the initial guess evaluation using the full of the model. So to conclude, just indicate that these two tools are in continuous developing within the Defacto project, and that we are currently working on extending the capabilities of the optimization function to solve global and multi-objective optimization problems. So that's all by my side, and thank you very much for your attention.
Thank you so much, Ruth. Perfect timing also for you. We received some questions, but I think it's better if we answer all of them at the end of the presentation during the Q&A. So for now, I would like to give the floor to Eduardo. He will be explaining tutorial and some guidelines about how to use these tools. So Eduardo, the floor is yours.
Yes, I'm going to share the video now. Can you see the video player?
Yes.
Yes.
Okay, great. So yeah, for those of you, I introduced myself earlier, but for those of you who joined late, my name is Eduardo Janet, and I'm a researcher at Universidad Polytechnic de Madrid. And I will be presenting this video tutorial in which we will quickly run through the setup and usage of the Defacto open source software available at the project website. Starting with a P4D time adaptive reduced order model tool, we will first access the Defacto project website, and then we will select the corresponding option under the software drop-down menu. In the opening page, we will start a download of the Docker image of the tool by clicking on the download button and proceeding to confirm the download and the successive pop-up pages that come up. And additionally, the P4D download page shows a brief description of the software tools and includes links to 3 useful resources: Docker installation guide, the HTML documentation of the code, and a guided tutorial of the usage of this tool. After the download of the Docker image is complete, we will proceed to its setup in our system. For that, we will first open the installation guide available in the download page. And note that in this video tutorial, the installation of Docker itself is omitted for the sake of brevity, but all the necessary information across operating systems can be found in this guide. We will start by opening a terminal in our system, and we will create a local folder, which will be used to share files between the Docker container and our system. Then we will proceed to load the downloaded image to the Docker daemon by typing the command line specified in section 2 of the Docker installation guide. Once this image is loaded, we can check that it has been correctly loaded into our system, and we can proceed to create the container from this image by typing the command line specified in the section 3 of this installation guide. So we will specify the desired container name, as well as the path to this shared folder that we just created locally. And finally, we will specify the name of the image that we just loaded and execute this command. After the execution of this command, a container console will automatically open. So now we will do a quick file structure walkthrough of the container that we created. Inside the home directory of this container, the P4D ROM directory contains all the necessary files to use the software tool. This is a main Python script to run the simulations, a data directory containing the required inputs, and the code, source, and documentation directories. We will now look into the data directory, and we will start focusing on the subfolder containing the cell model data files, consisting of a JSON file describing the cell model parameters and some additional text file describing OCB curves that also serve as inputs to the model. If we now take a look into this params.json file, we can see a structured definition of all morphological and electrochemical properties of the different components and materials of the cell. So there's the separator, the electrodes, and the current collectors, and so on, as well as the arrangement of this component in our cell or battery. Inside this data directory, the adapt dict.json file contains the definition of a small set of parameters that govern the time adaptive algorithm. And on the other hand, the sim.dict.json file holds the definition of simulation parameters, such as the relative paths to the data directories with respect to the main Python script, cell discretization options, active models, and so on. The store delay parameter sets the time step interval used to write the solution to XDMF and HDF5 output files. So we will set this value to 1 so that these files are generated and we can easily view a 3D representation of our solution. And after saving these changes, we will proceed to run this main adaptive script, which will launch the simulation of the P4D-ROM. After the simulation is completed, the log will show the total elapsed time of the simulation, and additionally, some basic yet valuable information regarding the time adaptive strategy, such as the number of degrees of freedom solved by each subsequent reduced order model, the error estimation that triggered the stopping criteria, time steps solved by each call to the reduced and full order models, and so on. After completing the simulation, a results file directory is created, and now we can copy it to the container shared folder for easily local manipulation through that folder we created earlier. So once we've copied these files, we can go to our system, open that shared folder that we just created, and view what's inside these results. The first thing that we're going to see is this image file created by default, which shows the cell voltage curve and some details of which fractions of the simulations have been run by the full and reduced order models. And there's also a second default .p file that has been generated. This file can be open in Python. As we're seeing, we are opening a Python console. We need to import the pickle package or module. And now we can open this .p file as a binary file with Python and use the pickle package to load it into a dictionary type variable, like we are seeing on the video. After this is done, we can inspect the keys of this dictionary containing all the results of the simulation, and we will start looking into what's in the mesh field. So the mesh field basically contains all the information necessary to reconstruct a mesh, such as the position of all the degrees of freedom, the degrees of freedom contained in each subdomain, interface, and so on. We're not going to look into it in too much detail, but all the information required is there. And also there's all the variable distributions across the degrees of freedom of the mesh and time stored in this .p file. Now we're going to exit and we're going to proceed to open a 3D post-processing tool. We have chosen ParaView for this tutorial since it's possibly one of the most well-known free open source 3D post-processing and visualization apps out there. So once we're in ParaView, we can load the generated XDMF results file into the application. And now we're going to be able to visualize the distributions in space and time, amongst many other operations, of all these variables that the problem's been solving. Now we're seeing the concentration at the surface of the active particles. And if we hit the play button, we can see the evolution in time of this variable. So this is just an example of what we could do when post-processing our results with a 3D visualization program. Now we move on to the downloaded setup of the optimization tool by entering the corresponding software page in the Defacto project website and clicking again the download button in the page, much as like we did before. This page also contains a brief description of this tool, as well as links to the additional resources, well, analogous to those we saw earlier. So the installation guide, code documentation in HTML format, and a guided tutorial for an optimization example. After the image is downloaded, again, like we did before, we can open a terminal in our system and load this this image file into our Docker daemon. In this case, it will take a little longer than the previous example. And once the image is loaded, we can check that it shows in the list of available images, and now proceed to the creation of a new container for these optimization tool, running the same command line we used before, but now giving a new name to our new container, linking again the shared folder in our local system to the one inside the container, and finally specifying the name of the image from which the container is going to be created. So again, after executing this command line, a console will start running on the newly created container, and we can proceed to a quick file structure walkthrough. All the necessary files in this container are contained in the opt p4d-rom directory. We step into this directory and we can observe the same file structure we saw for the p4d reduced order model tool, consisting of the main Python scripts and the data, source, and documentation directories. Inside the data directory, we can see the same file structure we saw before, but with one exception, which is an additional opt-dict file, which contains all the parameters to configure the optimization problem, such as which parameters are we going to be working with, their bounds, the paths to the data directories, and so on. We can now proceed to run this, the main optimization script. And once the optimization is complete, the resulting log will show some general information about the usage of both full and reduced order model through the process, including values of the objective function and their derivatives with respect to the optimization parameters in each iteration, and the elapsed time in each evaluation. And finally, a summary of the complete optimization problem is presented when the stopping criteria is met, which in this case, it has been only 3 iterations to find the optimum value of the objective function. And with this, we have reached the end of the video tutorial. It's been, I hope this quick start guide has provided a general idea on how to perform basic simulations and solve optimization problems. And in case you have any doubts regarding the use of the tools, you can ask us questions, but please remember that, as we have seen during the tutorial, the additional resources available in the download pages of both tools contain guided tutorials in which the format and structure of the input files are detailed, and also the HTML documentation of the different packages serves as an API guide for those of you who would like to develop your own implementation based on the software packages that we have developed. And with that, I think we can conclude this tutorial part of the webinar. So I'm going to stop sharing.
Thank you so much, Eduardo. Also perfect timing. I think now it's time to move to the interactive sessions. I just sent to you through the chat the direct link to the Mentimeter activity, but let me share my screen just to give you some indications about how to. Okay, so the idea is that you grab your phone, then you go to www.menti.com, and then you enter this code that I can, that you can also put it in on the Mentimeter website, and then you will be seeing the question that we are conducting, or you can just directly click onto the link that I sent, and just in case, I will copy also this code, and I will send you through the chat to make sure that you have the code. And if you have any doubts, please feel free to ask me directly through the chat. So let me open the. Okay, I think some of you already are answering the question. Let me share the screen too, so everybody can see the results. Okay, so The first question was, in what battery value chain related sector do you work in? And we are getting a lot of answers, but we can see that most of the answers are in the framework of research, simulation, electrode manufacturing. We also see some other answers like modeling, design, characterization, management, consultancy, Second Life, automation, cell manufacturing. Okay, I don't know if if you are waiting any other answer. But yeah, I think at a glance, we can see that simulation and research are the most frequent answer. Okay, so moving into the next question is which cell battery simulation optimization software are you using? And I think here you have a few questions, or I think it's a word cloud answer. Okay. So we start to see some answers. We have Batmo, Python, MATLAB, Python, the Defacto software, CIDETEC, Amesim, and Star CCM. Okay, so it seems that the most used software is Python. Let's see if we have any other answer. Okay, if not, I think we can semi-empirical models, COMSOL. Okay, good to know. This is also very useful for us. Let's move to the next question, which is, if your organization is planning to invest in cell battery simulation optimization software in the next 2-3 years, which tool are you considering, or which tools? Let's give a few seconds, so take your time to enter your answers. Okay, we start here. We start seeing some of the answers. So the first one is not sure. We also have the audit. Okay, it's moving a lot. So don't know. So it seems that there is a lot of doubts regarding which tools you will be considering. But we see Python, COMSOL, open software, Python-based, Defacto tools as well. So let's wait if we have any other answer. Okay, so it seems that most popular is, according to your answers, Python-based. So it's good to know. Also artificial intelligence. Okay, good to know. It seems that it's a trend to use artificial intelligence. Well, I guess it's artificial intelligence, or no, actually it's IA, artificial intelligence. So let's move to the next questions, which is, would your organization consider paying for services related to the customization of a code to suit your specific needs? I hope so. Okay, not sure. Here we see maybe yes. If it had a good impact. So maybe yes. So according to the answer is like a so-so. Okay, let's see if we have any more answers. Why not? Depends on customer. Not at the moment. Okay, so I think we are not getting more answers. So I think we can move to the, I think there is 2 more questions. This one is regarding the simulation optimization software currently available in the market. What are the gaps identified in order to cover all your needs? All these questions help us to find exploitation routes and also to identify potential needs. Okay, so we start to see flexible, adaptable SW is the first answer. Complete process chain. User-friendly, difficult to use. So I guess user-friendly and difficult to use are in the same line, so more intuitive design. Okay, we have a lot complex and large cells. We have user-friendly, new chemistries, reduce calculation effort. Okay, we have a lot. I'm not sure if I'm gonna read all of them. To narrow a focus, unclear data methodologies. Also, another gap is multi-scale, reduce calculation effort, battery degradation, complexity of materials, standards. Okay, so as a trend, we could identify that the design or the software that are currently available are not user-friendly, as well as some technical answer that we have received. Okay, so this is a very nice feedback. Thank you. And we have the last question, which is, after seeing the benefits of the Defacto P4D software, do you foresee this solution could substitute other tools you are currently use? Okay, we have a big yes. We are glad to see. Again, okay, it's getting even bigger, so thank you. Another feedback is complementary. For sure, it will be. A test will confirm. You can also let us know. I just copy the email, the Defacto email on the chat. So in case you want to let us know or to give us some feedback regarding the tool. First one to use, don't know. Okay, let's wait a few more seconds. Okay, so it seems that we already have some answers. Great, I think this was the last question. So thank you so much for participating. So let me now go back to my presentation. And I think we have still time to answer some. I think I also received 2 questions. Oh, let me open the presentation again. So here. Okay. So basically I received 1 question. The first one was, can we have these presentation slides? As I said, this webinar is being recorded and I will be shared and posted on YouTube and also on the Defacto website. But if specifically you want to have any particular presentation, you can also let us know in the, you can send me an email through the project email. I already put the mail on the chat. So it's info@defacto project.eu. So you can send us there any particular questions or this require, and we will send you the presentations. But another question that we have, and this is more technical, this is maybe more addressed for you. I think it was for during the Ruth presentation. Is do they use console software to do CFD DEM analysis?
No, Pablo, maybe the question is for me because it's related to
Okay.
the manufacturing. So no, they're using open source. I don't remember exactly the specific tool, but if you post your email account, and then I could give you this information in particular to the CFDDM approach for the trial step.
Okay.
I
Yes, I
think
can
that
send you. I can send you the question and the person who asked it, Ellie.
I think they use also OpenLB for lattice Boltzmann. If the question is concerning the modeling of the filling.
No, but yeah, okay, but the question was for the CFD-DM, no?
CFD DEM analysis.
Sorry.
Yeah. So yeah, this is a TU Braunschweig work, so I could collect this information and give you.
I will resend you this the question. Another question is like, how can we get a training course from Defacto? Is there any possibility to involve in a training? Well, we are developing a training section on the website, which will be available probably during September, October. There you will have a lot of resources that is actually containing information about these tools and other tasks that has been developed and conducted through the project. So yes, I invite you to follow our social media channels to stay tuned because we will probably launch it in September, October latest. So from there, you will have the opportunity to learn a little bit more about the project in let's say in a training way. We will develop e-learning materials, some videos, and some training courses that maybe cover your needs. And yes, that was actually all the questions that I received. Let me check one more time the chat. But we don't have any other questions. Again, if you want to ask any particular thing, you can also email us through the project email, and I will address your question to the speaker. Okay, so we are also perfect timing. We are on time. So I would like to thank all the speakers and all the audience that have attended to the webinar to participate and to give us such as great feedback through the Mentimeter activity. It's been a pleasure to me to host this webinar, and I would like to thank also the speakers to make it so easy to coordinate. As I said, I invite you to follow our social media channels to stay tuned when we will upload these recording of the webinar. And please, if you have any kind of questions or comments, feel free to email us. So that's all for me. Thank you so much. And I hope to see you soon.